7 seconds. Not 7 minutes. Not 7 hours. 7 seconds. In 7 seconds, a machine with no wheels, no engine, no fuel, floating above a track on nothing but invisible magnetic force, reached 650 kilometers. Per HR, Japan held that record for 10 years. China erased it in the time it takes to exhale. Welcome back to the channel. Today we are looking at one of the most significant breakthroughs in the entire history of high-speed transportation ever attempted by human engineering. It is called the Donghu Laboratory Maglev Sprint Test, and on the 17th of June, 2025, it changed everything we thought we knew about how fast a vehicle could accelerate on land. This is not just a fast train. This is not just China beating a record. This is a fundamental rethinking of what speed means, how you build for it, how you measure it, how you control it, and how you stop it. Because stopping something moving at 650 kilometers per HR is in many ways harder than accelerating it there in the first place. This is not just a test run on a track. It is a proof of concept that shatters a decade of assumptions. It is an engineering statement that says everything you thought required 42 kilometers of track, we did in 1. Think about that for a moment. Japan's record, the record that stood since the 21st of April 2015, the record that was certified by Guinness World Records, the record that the entire world of rail engineering acknowledged as the ceiling of what was physically possible, was set on a 42.8-kilometer test line near Mount Fuji, a line that took years to build, billions to fund, and decades of research to even justify a 7-car train. 49 JR Central employees on board 10.8 seconds above 600 kilometers per HR. And the crowd that had gathered along the track erupted. China just did it better, on a track that is 42 times shorter. Before we continue, make sure you subscribe to the channel and hit the notification bell, because the story we are about to tell you does not end at 650 kilometers per HR. It ends, or rather it begins, at 800, and then possibly 1,000. Stay with us until the end, because the final section of this video contains something that will permanently change how you think about the future of travel on this planet. At first there was only the problem, not a track, not a laboratory, not a prototype, just the problem clean, enormous, and seemingly unsolvable. The problem was this: to test a vehicle at extreme speeds, you need extreme distances. That is the physics. You cannot accelerate something to 600 kilometers per HR in 100 meters. The forces involved would tear any mechanical system apart. The energy required would overwhelm any conventional propulsion, and the braking distance alone, the distance you need to slow something from that speed back to zero safely, would consume an enormous length of track all by itself. This is why Japan built 42.8 kilometers of test line. This is why most serious high-speed maglev research facilities around the world work with test tracks measured in tens of kilometers, not hundreds of meters. Long tracks are not a luxury. They are, by every conventional understanding of physics and engineering, a necessity. If you try to accelerate too hard, the forces acting on the vehicle become dangerous to the structure of the vehicle itself, to the guidance systems that keep it aligned, to the sensors that monitor its position, and to the electromagnetic infrastructure. If you try to brake too hard, you generate enormous heat, enormous stress, and enormous risk of system failure at exactly the moment when the vehicle is moving fastest. If you build a short track and simply accept that the vehicle will hit the wall at the end, you have not built a test facility. You have built a very expensive way to destroy prototypes. This was the wall that the engineers at Donghu Laboratory in Hubei Province decided to walk straight through. Their solution was not to find a longer piece of land. It was not to compromise on the target speed. Their solution was to fundamentally reinvent the physics of how you get a vehicle to extreme speed, and then get it back in the shortest possible distance. So the solution was not simple. It was not a bigger motor or a stronger magnet. It was a complete rethinking of the relationship between propulsion, levitation, braking, and control compressed into 1,000 meters and executed with a positioning accuracy of 4 millimeters at speeds that would outrun most commercial aircraft. Let us start at the very beginning. Let us start with what maglev actually is and why it matters. Magnetic levitation is, at its core, the removal of contact, the removal of wheels on rails, the removal of axles, bearings, rubber, metal grinding against metal. Every conventional vehicle, whether it is a car, a train, a truck, or a motorcycle, is in constant physical combat with the surface it travels on. That contact creates friction. Friction creates heat. Heat creates energy loss. And at high speeds, that friction does to just slow you down. It becomes a structural threat. The faster you go, the more violently the wheels interact with the track. The more the vibrations compound, the more the mechanical stress multiplies. This is why conventional high-speed trains have an effective ceiling. Not because the motors are not powerful enough, but because the contact between wheel and rail becomes increasingly catastrophic as speed increases. The vehicle floats. It does not touch the guideway. There is a gap measured in millimeters between the bottom of the vehicle and the surface beneath it. And in that gap, maintained by precisely calibrated magnetic fields, the vehicle experiences no friction from the ground at all. The only resistance it faces is the air. This is why maglev can go faster than any wheel-on-rail system ever could, not because of better engines, because of the absence of contact. But here's what most people do not understand about maglev. There are fundamentally different ways to achieve levitation, and they produce radically different performance characteristics. Japan's 6 Maglev, the system that held the world record, uses superconducting electromagnets. These are coils of wire cooled to extraordinary temperatures, near absolute zero, using liquid helium, so that they lose all electrical resistance and can carry enormous currents that generate enormous magnetic fields. The vehicle floats inside a U-shaped guideway, pushed and pulled by a linear motor running along the track walls. It is a breathtaking system, enormously powerful, enormously complex, and enormously expensive both to build and to maintain. Japan has been developing this technology since the 1970s. The 42.8-kilometer Yamanashi test line, where the 603 kilometers per h record was set, was constructed beginning in 1990. The record run took place in 2015. That is 25 years from groundbreaking to Guinness certificate. China's Donghu system is different. It uses what engineers describe as like-pole repulsion, the same fundamental principle that every child encounters when they try to push the same poles of two magnets together and feel them push back. The vehicle is pushed upward by the repulsive force between magnets of the same polarity on the vehicle and on the guideway. This is combined with an electromagnetic propulsion system, a linear motor that drives the vehicle forward with extraordinary force. No supercooling, no liquid helium, no decades of cryogenic engineering, just magnetic repulsion and electromagnetic drive, pushed to their absolute limits of precision and power. And the key to making this work on a 1-kilometer track, the key to the entire breakthrough, is something that Lai Waikao, the director of the High-Speed Maglev Electromagnetic Propulsion Technology Innovation Center at Donghu Laboratory, calls short-distance boost technology. Think of it this way. Imagine a pinball machine. You pull back the spring. You compress it. You store enormous energy in that compressed spring. And then you release it. All at once, and the ball rockets down the table with a force that no amount of gentle pushing could ever achieve. The entire energy transfer happens in a fraction of a second. That is the philosophy behind the Donghu sprint approach. Not a long, gradual acceleration over tens of kilometers. A concentrated, violent, perfectly controlled release of energy over the shortest possible distance. To make this work, you need 3 things to be simultaneously true. The propulsion system must be able to deliver enormous force in a very short window. The levitation system must maintain a stable controlled gap between the vehicle and the guideway throughout that violent acceleration, because even a millimeter of misalignment at 650 kilometers per HR is catastrophic. And the braking system must be able to absorb all of that kinetic energy, all the speed and mass of the vehicle within the remaining distance of track, without applying forces so violent that they damage the vehicle or the infrastructure. This was not just an engineering challenge. This was 3 simultaneous engineering challenges, each of which was independently enormous, and each of which had to be solved in a way that did not conflict with the other 2. Let us walk through exactly how they did it. The track itself, the 1,000-meter test line at Donghu Laboratory, is not a simplified version of a longer track. It is a purpose-built system, designed from the ground up for short-burst extreme acceleration. Every centimeter of that guideway is a precision instrument. The surface tolerances are measured not in millimeters but in fractions of millimeters. The alignment of the magnetic coils that run along the guideway walls must be exact to within tolerances that would make a Swiss watchmaker nervous. Because at 650 kilometers per h-hour, the vehicle is covering approximately 180 meters per second. A misalignment that would be invisible to the naked eye, a deviation of fractions of a millimeter in a coil position, can translate into a destabilizing force on the vehicle that compounds faster than any control system can correct. So before a single test run was conducted, before the prototype vehicle was even placed on the guideway, the track itself underwent calibration procedures of extraordinary rigor. Every coil surveyed, every magnetic field measured, every alignment verified, every component of the power delivery system tested under load. The track had to be perfect before the vehicle touched it, because the vehicle was going to trust that track with its structural integrity at speeds where there is no margin for error. Then came the vehicle itself. The test vehicle weighing 1.1 tons is not a passenger car. It is not a prototype of a future commercial train. It is a purpose-built research platform, a chassis designed specifically to demonstrate that the propulsion and levitation technology works, that it can reach the target speeds, and that it can do so safely and repeatably. Its design is the result of solving a list of simultaneous engineering constraints that includes aerodynamic drag minimization at extreme speeds, structural rigidity sufficient to withstand the propulsion system, sensor integration for real-time position and velocity monitoring. Every gram of that 1.1 tons was accounted for, not estimated, accounted for. Because the energy calculations that determine how much propulsive force the system needs, how much braking force it must generate, and how much distance is required for each, those calculations are sensitive to the mass of the vehicle. A heavier vehicle needs more energy to accelerate to 650 kilometers per h, or a heavier vehicle carries more kinetic energy at that speed, and therefore needs more braking force and more stopping distance. The engineers at Donghu were working with 1,000 meters total, 600 meters for acceleration, 220 meters for braking. That leaves a very narrow margin. Every kilogram of the vehicle's mass was part of the engineering equation. The propulsion system, the linear motor running along the guideway, is the heart of the entire achievement. A linear motor is conceptually a rotary electric motor that has been unrolled and laid flat. Instead of a spinning rotor inside a stator, you have a moving element, the vehicle traveling along a fixed element. The track? The electromagnetic coils in the track are energized in sequence, creating a traveling magnetic wave that pushes the vehicle forward. The faster you can switch the current in those coils, the higher the frequency of that traveling wave, the faster the vehicle accelerates. But there's a problem. At extreme acceleration rates, the power demands of the linear motor spike to levels that would overwhelm a conventional electrical grid connection. You cannot simply plug this system into the national power network and pull the energy you need in real time. The rate at which energy must be delivered to the coils during the acceleration phase far exceeds what any standard electrical supply infrastructure can provide instantaneously. The solution is energy storage, specifically the kind of transient high-power energy storage that can be charged slowly over minutes or hours and then discharged in seconds with extraordinary intensity. Capacitor banks, high-power battery systems, energy storage technologies that are designed not for continuous delivery, but for explosive. Short duration, released, the power system charges between runs. It accumulates energy, and then at the moment of launch, it releases that stored energy through the linear motor coils with a speed and intensity that produces the propulsive force required to push 1.1 tons to 650 kilometers per h, hour in 600 meters. This is not a technology that simply existed off the shelf. The development of energy, storage and power electronics capable of delivering this kind of performance at the switching speeds required, at the power levels required, with the reliability required for a repeatable test system was itself a significant engineering achievement. One of several that had to be solved before the record run was even possible. Then came the levitation system. In China's Donghu approach, the vehicle floats above the guideway through, like pole magnetic repulsion, but floating is a dangerously casual word for what is actually happening. At rest, the vehicle sits a specific distance above the guideway, a gap that is determined by the balance between the vehicle's weight and the repulsive magnetic force pushing it up. But at speed, especially at 650 kilometers per h, the vehicle is not at rest. It is subject to aerodynamic forces that change with velocity. It is subject to the effects of the propulsive electromagnetic field, which interacts with the levitation field. It is subject to any microscopic imperfection in the guideway surface. All of these forces act on the vehicle simultaneously, trying to push it up, push it down, push it sideways, rotate it, and all of these disturbances must be corrected continuously in real time by the control system. This is where the 4mm positioning accuracy becomes not just impressive, but essential. The system must know at every instant during the run exactly where the vehicle is relative to the guideway, not approximately, to within 4mm at 180 meters per s. This requires sensor technology that can take position measurements thousands of times per second, feed those measurements into a control algorithm that calculates the required correction in microseconds, and then actuate the correction through the magnetic control systems before the vehicle has moved far enough for the error to compound. Without that 4mm precision, the vehicle's trajectory becomes unpredictable. At 650 kilometers per h, an uncorrected lateral deviation of even a centimeter, left unchecked for a fraction of a second, can result in contact between the vehicle and the guideway. And contact at that speed is not a bump. It is a catastrophic structural failure. This is why the precision measurement and positioning system is not a supporting feature of the Donghu test. It is the system upon which every other system depends. The propulsion cannot work without knowing where the vehicle is. The braking cannot be initiated at the right moment without knowing the vehicle's exact position and velocity. The levitation cannot be controlled without continuous feedback on the gap between vehicle and guideway. Every measurement mattered. Every sensor mattered. Every microsecond of control loop response mattered. Then came the braking. This is the part that most coverage of the Donghu test glosses over. Everyone talks about 650 kilometers per h. Almost nobody talks about 220 meters. The test vehicle, moving at 650 kilometers per h, which is approximately 180 meters per second, was brought to a complete safe stop within 220 meters. Using electromagnetic boost brakes. Let us sit with that for a moment. The vehicle enters the braking phase at 180 meters per second. It must reach zero or near zero within 220 meters. That deceleration rate is not gentle. It is not comfortable. It is not the kind of gradual slowing you experience on a commercial train. The forces involved in decelerating a vehicle that rapidly are enormous, and those forces act on the vehicle structure, on the guideway, and on the control systems that must maintain the levitation gap and vehicle alignment throughout the braking process. Because a vehicle that loses magnetic stability during braking at 650 kilometers per h does not simply stop, it becomes a projectile. The electromagnetic braking system works by reversing the principle of the linear motor. Instead of using the electromagnetic field to push the vehicle forward, it uses the field to resist the vehicle's motion, converting the vehicle's kinetic energy back into electrical energy, which can be recovered and returned to the storage system. This is regenerative braking. It is elegant. But at these deceleration rates, the power being generated during braking is enormous, potentially as large as the power consumed during acceleration. Managing that regenerated energy, ensuring it does not overwhelm the storage system, ensuring the braking force is applied smoothly and controllably, and does not induce oscillations in the vehicle required the same level of engineering precision as the propulsion system itself. The braking is not just the end of the run. The braking is proof that the system works, because a system that can only accelerate is not a transportation technology. It is a weapon. The ability to stop safely, controllably, within 220 meters from 650 kilometers per HR is what transforms this from a stunt into a platform. And that word platform is exactly how Lai Weiqiao describes it. This is not a one-time demonstration. This is a repeatable test platform. The same technology, the same infrastructure, the same 1-kilometer track can be used for run after run after run. Charging the energy storage system between runs, checking the vehicle alignment, verifying the sensor calibration, and then launching again. The fact that the track is only 1 kilometer long means the facility footprint is manageable. The facility can be built on a university campus, inside a research park, at a fraction of the cost and land area required for a 42-kilometer test line. This is the second revolution hidden inside the 650 kilometers per h number. Not just that China achieved the speed, but that China demonstrated you can achieve world record Maglev speeds on infrastructure that is accessible, repeatable, and scalable in a way that Japan's Yamanashi, lie magnificent as it is, simply cannot match. Now let us place this in context. Let us talk about what Japan built, what it cost, and what it meant. Because without understanding the mountain the Donghu Laboratory climbed, you cannot fully appreciate how high they climbed. Japan's superconducting Maglev program is one of the great engineering commitments in human history. It began not in 2015, when the record was set. It began in the 1970s. That is not a typo. The foundational research that led to the L0 series train and the 603 kilometers per h record on the 21st of April 2015 started more than 4 decades before that record run. 4 decades of refinement, of dead ends, of rebuilt prototypes, of expanded test tracks, of cryogenic engineering, of power electronics development, of aerodynamic optimization, the Yamanashi Maglev test line, the 42.8-kilometer track near Mount Fuji, where the record was set, began construction in 1990. The first test vehicles were delivered to the depot in 1995. The initial priority section of 18.4 kilometers was completed in 1997, and the full 42.8-kilometer extended line was the result of years of additional construction. After that, the 7-car L0 series train that set the record is a magnificent machine. It carries 49 JR Central employees on that record run. It hovers 10 centimeters above the guideway, 4 inches suspended by superconducting magnets cooled to temperatures close to absolute zero. It spent 10.8 seconds traveling above 600 kilometers per h-hour during the record run, covering 1.8 kilometers in that window. The crowd of approximately 200 train enthusiasts gathered along the route erupted when the train broke through 600. It gave me chills, one witness told NHK. It's like I witnessed a new page in history. They were right. They did witness a new page. What they did not know was that the next page would be written 10 years later, in a laboratory in Hubei Province, on a track that their entire record-setting run could fit inside twice. Japan's record was 603 kilometers per HR China. Donghu test reached 650 kilometers per HR. That is a difference of 47 kilometers. Per HR in percentage terms, that is roughly a 7.8% improvement in top speed. A meaningful number, an impressive number, but not in itself a revolutionary number. The revolution is not in the 47 kilometers per HR. The revolution is in the 41.8 kilometers of track that China did not need. Because here's what that means for the future. If you want to test Maglev technology at extreme speeds, and you need 42 kilometers of track to do it, then your research program requires an enormous capital investment in infrastructure before you can even begin testing. You need to acquire the land. You need to build the guideway. You need to install the power systems, the control systems, the monitoring infrastructure. You need to maintain all of that. And you need to do all of that before you have demonstrated that any of the underlying technology even works at the speeds you are targeting. The knowledge comes later. China's Donghu approach inverts that. The infrastructure is 1 kilometer. It is compact enough to be built as part of a laboratory complex. It is cheap enough relatively to be repeated. And because it is short, the cost of a failed test run is not the destruction of 42 kilometers of guideway. It is the replacement or repair of a vehicle and the reset of a 1,000-meter facility. You can run more tests, you can iterate faster, you can learn more, in less time with less money and on less land. This is why Li Weikao said, and this is a direct quote, that the technology developed at Donghu is already being promoted and applied in multiple scientific research devices. The platform is not just for maglev trains. The short-burst electromagnetic acceleration and braking system has applications in aerospace testing, in materials science, in defense research, in any field where you need to subject an object to extreme acceleration and deceleration forces in a controlled environment. The 1-kilometer Donghu track is in essence a universal extreme. Acceleration research tool, the 650 kilometers per h maglev sprint is its most spectacular demonstration. But it is not its only purpose. Now let us go even deeper, because there is a layer of this story that almost no coverage has addressed, and it is perhaps the most important layer of all. The question is not just how fast the Donghu vehicle went. The question is what it means that a 1.1-ton test sled, not a passenger train, not a full-scale prototype reached 650 kilometers per HR on a 1-kilometer track. What does that tell us about the underlying physics? And what does it tell us about the path from this test to something a human being could actually ride? The gap between a test sled and a passenger train is vast. We should be honest about that. The Donghu vehicle is not a train. It is a research platform, a chassis, essentially equipped with sensors and instrumentation designed to validate the propulsion and levitation technology and to demonstrate that the speed and braking targets are achievable. It carries no passengers. It has no interior. It is optimized for one thing, proving the concept. A passenger train is a completely different engineering challenge. It must carry dozens or hundreds of people safely. It must maintain those speeds over extended distances, not 600 meters, but hundreds of kilometers. It must be able to handle curves, inclines, variations in weather, variations in load. Its doors must work. Its pressurization must be maintained. Its emergency systems must function at speed. Its noise levels must be manageable for human occupants. Its ride comfort must not induce motion sickness or structural stress on passengers' bodies over a journey of an hour or more. None of that is solved by the Donghu test. And the engineers at Donghu know that. This is why Li Weikao describes the test track as a platform, not a product. This is why the stated goal of 800 kilometers per h-hour is a test target, not a commercial operating speed. The path from 650 kilometers per h-hour on a 1-kilometer sled track to a commercial maglev passenger service at, say, 500 or 600 kilometers per h-hour, that path is long. It involves solving aerodynamics at scale, vacuum tube infrastructure, station design, safety certification, network economics, and dozens of other engineering and regulatory challenges. But here is what the Donghu test does do. It proves the propulsion works. It proves the levitation is controllable at these speeds. It proves the braking is achievable in a meaningful distance. It proves the positioning and sensing systems can operate at 650 kilometers per h-hour with 4mm accuracy. These are the core physics. These are the fundamental validations. Without them, everything else is speculation. With them, everything else becomes an engineering problem. Difficult, expensive, time-consuming, but solvable with known tools and known methods. Japan spent 25 years getting to 603 kilometers per h-hour on a 42-kilometer track. China has now demonstrated 650 kilometers per h-hour on a 1-kilometer track. These are two different approaches to the same destination. And the fact that China achieved their result with a fundamentally different technology, not superconducting electromagnets cooled with liquid helium, but like pole repulsion and high-power linear motors, means the field of ultra-high-speed maglev is no longer a single narrow corridor with one team in it. It is a race. And for the first time in 10 years, that race has more than one competitor at the front. Imagine standing at the end of that 1-kilometer track, not in the control room, not watching on a screen. Standing at the end, behind the safety barriers, looking down the length of the guideway, 600 meters away. The test vehicle sits motionless. 1.1 tons of precision engineering, every sensor active, every magnetic coil in the guideway charged and waiting. The energy storage system holding the equivalent of a brief but violent electrical storm ready to release. 3, 2, 1. In the first second, the vehicle moves. Not dramatically, it lifts just millimeters off the guideway. As the levitation field activates, the gap between the vehicle's underside and the guideway surface opens 4 millimeters of pure magnetic force, and then the propulsion engages. In the second, the vehicle is already moving faster than a professional sprinter runs. The linear motor is driving it forward with a force that presses the vehicle against the air in front of it, like a fist pressed against a wall. The aerodynamic drag is building not linearly, but exponentially. The faster the vehicle goes, the harder the air pushes back. In the third second, the vehicle has passed 200 kilometers per hour. It is moving faster now than any car on a German autobahn. The sound it makes is not the thundering roar of a jet engine. It is a rising electric whine, the sound of the linear motor coils switching at ever-increasing frequency. A sound that climbs in pitch as the vehicle accelerates. Like a turbine spooling up in the 4th and 5th seconds, 300 kilometers per are 400. The vehicle is now outrunning a Shinkansen bullet train at its operational maximum. The air displacement around the vehicle is producing pressure waves that travel ahead of it down the guideway, compressing the air in the narrow space. The control system is making thousands of corrections per second to the levitation gap, to the lateral alignment, to the power delivery in each coil section. Invisible adjustments, each one smaller than a human hair's width. In the 6th second, 500 kilometers per h, the vehicle is approaching the speed that Japan SL0 series commercial service will operate at when the Chua Shinkansen opens. The speed that JR Central spent decades engineering toward for human passengers. The Donghu vehicle has reached it in 6 seconds, and then the 7th second, 650 kilometers per h. The vehicle blurs past the measurement markers at the 600-meter point. The sensors confirm 650. The positioning system confirms stable. The levitation gap holding. The vehicle is flying, not metaphorically. In every physical sense that matters, it is flying, floating above the guideway on a cushion of magnetic repulsion, propelled by electromagnetic force, moving at a speed that most commercial aircraft do not reach until they are well into their takeoff roll. And then the braking begins. The braking begins at the 600-meter mark. Not with a screech, with a reversal. The same linear motor that drove the vehicle forward now becomes its anchor. The electromagnetic field that was pulling the vehicle down the track switches its polarity. Not all at once, but in a precisely calculated sequence, and begins to resist the vehicle's motion. The kinetic energy that took 600 meters and 7 seconds to build up is now being extracted, absorbed, converted back into electrical current, and fed into the recovery systems. The vehicle decelerates. But here is what you must understand about decelerating something from 650 kilometers per h. The forces acting on the vehicle during braking are not smaller than the forces during acceleration. In many ways, they are larger. During acceleration, the electromagnetic field is working with the vehicle, pushing it, guiding it, giving it energy. During braking, the electromagnetic field is working against the vehicle's momentum, and momentum at 650 kilometers per h. In a 1.1-ton object is an enormous physical fact. It does not want to stop. Every kilogram of that vehicle, every meter per second of its velocity, represents stored energy that must go somewhere into the braking system. into the recovery circuit, into heat, into mechanical stress on the guideway and the vehicle structure. The engineers at Donghu calculated that the vehicle could achieve safe braking within 220 meters. That calculation is not a guess. It is the result of precise modeling of the deceleration forces, the energy recovery capacity of the electromagnetic braking system, the structural limits of the vehicle chassis, and the maximum stress that the guideway and its coils can absorb during a full emergency stop from top speed. Every one of those parameters had to be right, not approximately right, exactly right. Because the track is 1,000 meters long, the vehicle reaches peak speed at 600 meters. That leaves 400 meters of track remaining. The vehicle must stop within 220 of those meters. The margin, the distance between the end of the calculated stopping zone and the physical end of the track, is not vast. The engineering has to be trusted completely. And it was. The vehicle stopped within 220 meters, from 650 kilometers per h-hour, clean, controlled, safe, within 4 millimeters of where the positioning system said it would be. That last detail is not decoration. That last detail is the entire point, because a system that stops a vehicle from 650 kilometers per h-hour within 220 meters is impressive. A system that does it while knowing at every moment during that deceleration exactly where the vehicle is within 4 millimeters, trusted to repeat, trusted to scale, trusted to one day carry human beings. Most people who pass through a train station see only the platform. They see the train, they hear the doors, they feel the gentle motion as the vehicle accelerates away. They do not see the electromagnetic coils embedded in the guideway beneath the track surface, each one positioned to tolerances measured in fractions of millimeters, each one connected to a power delivery system that switches current at frequencies far beyond anything visible to the human eye. They do not see the sensor arrays that run the length of the guideway, the systems that track the position and velocity of the vehicle thousands of times per second, feeding data to control bins that make corrections faster than any human reflex could ever match. They do not see the energy storage systems, the banks of capacitors and high-power electronics that charge slowly between runs and discharge in an instant with a force that lights the entire propulsion system like a struck match. They do not see the thermal management systems that handle the heat generated by the linear motor coils during acceleration. Because moving that much electrical current through those conductors at those switching rates generates heat, and that heat must go somewhere, must be managed, must be kept within limits that do not degrade the coil's performance or shorten their operational life. They do not see the structural analysis that went into every weld, every joint, every fastener in the vehicle chassis, the calculations that determined how much bending stress, how much torsional stress, how much vibration loading that 1.1-ton frame would experience during 7 seconds of extreme acceleration, and then 220 meters of violent deceleration, repeated run after run after run. They do not see the software, the control code that runs the entire system that govern the levitation gap, the propulsion setchery, the braking intensity, the sensor fusion, the fault detection, the emergency shutdown protocols. Software that must execute correctly, every time, with no tolerance for bugs in the sections of code that run during the active phase of a test, because a software fault at 650 kilometers per HR is not something you dap in the next version. It is something that ends the test vehicle's existence in approximately the time it takes to blink. They do not see any of this. What they see, what the world saw when the footage was released, is a blur. A vehicle that appears at one end of the frame and disappears from the other in less time than it takes to process what you are looking at. 7 seconds of motion, that look, on video. Almost casual, almost easy. Almost as if the machine simply decided to go fast and the track led it. None of it was easy. Every second of that run represented years of work. Now, let us talk about where this goes. Because the 650 kilometers per h test is not the destination. It is the departure point. Li Weichao stated clearly, in his interview with China Media Group following the test, that the Platform-S typical operating speed target is 800 kilometers per HR, and that the full construction of the Donghu high-speed track, meaning the extended complete version of the facility, was expected to be finished by the end of 2025. The 650 kilometers per h run in June 2025 was achieved on the existing 1,000-meter test section. The completed facility is designed to support the next phase, the push toward 800 kilometers per h. That number deserves a moment of consideration. 800 kilometers per h-hour is faster than the cruising speed of most commercial jet aircraft. A Boeing 737 cruises at roughly 850 kilometers per h-hour at altitude, a vehicle on the ground, in open atmosphere. Approaching that speed, the aerodynamic challenges alone become a different class of engineering problem. At 800 kilometers per h-hour, the pressure wave that builds up in front of the vehicle is not just a drag force. It becomes a structural and acoustic phenomenon. The compression of air ahead of the vehicle creates a shock front, not quite a sonic boom, because 800 kilometers per h-hour is still below the speed of sound in air at sea level, which is approximately 1235 kilometers per h-hour. But close enough that the aerodynamic behavior of the vehicle begins to exhibit characteristics that conventional subsonic aerodynamics does not predict well. This is why the engineers at Donghu and at other Chinese research institutions working on ultra-high-speed maglev are also researching low vacuum tube environments. If you reduce the air pressure inside the tube through which the vehicle travels not to a full vacuum, but to a partial vacuum, you reduce the density of the air the vehicle must push through. You reduce the aerodynamic drag, you reduce the acoustic shock effects, and you open the door to speeds that are genuinely aircraft. And a low vacuum tube, a maglev vehicle could theoretically operate at 1,000 kilometers per h-hour or beyond. China already has an experimental line in Datong in Shanxi Province, a 2-kilometer section that passed in kilometers per h-hour in a low vacuum environment. This is a different program from Donghu, but it is part of the same national direction. China is not pursuing one approach to ultra-high-speed transport. It is pursuing several simultaneously on parallel tracks using different technologies, targeting different speed ranges, with different time lanes. The Donghu sprint test is the most dramatic demonstration of that effort. But it is one node in a much larger network of research and development, and there is another dimension to this that goes beyond passenger transport entirely. Li Weichao said, in the aftermath of the June 2025 test, that there are numerous potential uses in civilian scenarios for the technology developed at Donghu. He said, the technology is already being promoted and applied in multiple scientific research devices. What does that mean in practice? It means that the short-burst electromagnetic acceleration system, the technology that took a 1.1-ton vehicle to 650 kilometers per h-hour in 600 meters, has applications beyond trains. Applications in materials testing, applications in defense research. The same principle that drives a maglev vehicle to extreme speed on a short track can be used to accelerate test payloads in wind tunnel simulations, to test the structural integrity of materials under extreme dynamic loading, to launch small vehicles or projectiles for research purposes. The Donghu track is, in essence, a ground-based linear accelerator. Its primary demonstration is a maglev speed record. Its potential applications extend far beyond rail transport. This is consistent with a broader pattern in how China has approached infrastructure and technology development. Build the platform, demonstrate the headline number, then let the platform serve multiple research programs simultaneously. The 1-kilometer Donghu track will not sit idle between speed record runs. It will be used continuously for component testing, for system validation, for research into the underlying physics of extreme electromagnetic acceleration. Each run produces data. Each TATFO informs the next run. Each improvement in the system's performance feeds into both the Maglev research program and the broader portfolio of technologies that the short-distance boost approach enables. Without that understanding, the Donghu test looks like a stunt, a record for a record's sake. With that understanding, it looks like what it actually is: the commissioning of a research infrastructure that will produce scientific and engineering value for years to come. Now let us place all of this in the broader context of what is happening in the world of high-speed transport. Japan's Chuo Shinkansen, the commercial maglev line that will connect Tokyo and Nagoya, has been under construction for years. Its construction cost is estimated at nearly $100 billion just for the stretch to Nagoya, with more than 80% of the route passing through costly tunnels. The planned commercial operating speed is 500 kilometers. Per HR, the Chuo Shinkansen will be the first commercial maglev line in the world to operate at those speeds when it opens. It is a colossal achievement of engineering and national commitment. But it has faced delays, it has faced cost escalation, and it will operate at 500 kilometers, per HR the same speed that the Donghu test vehicle surpassed in its fifth second of acceleration. China, meanwhile, already operates the world's fastest commercial maglev in daily service, the Shanghai Maglev, the Transrapid Line. Built by a joint venture of Siemens and ThyssenKrupp, connects Shanghai Pudong International Airport to Longyang Road Station, a distance of approximately 30 kilometers, in approximately 7 to 8 minutes, at a top speed of 431 kilometers per h-hour. That system has been running since 2004. It is right now the fastest commercially operating train on Earth. And it is a German technology built in China, a fact that gives some context to how far China's own domestic maglev research has come since then. From operating a German, designed 431 kilometers per h commercial system in 2004, to building its own indigenous research platform that demonstrates 650 kilometers per h in 2025. That is 21 years. And within those 21 years, China has also built the world's largest high-speed rail network, approximately 45,000 kilometers of track, a network that dwarfs every other country's high-speed rail infrastructure on Earth. While other nations debated, planned, delayed, and occasionally canceled their high-speed rail ambitions, China built thousands of kilometers of track, hundreds of stations, dozens of high-speed lines connecting cities that previously took days to reach by conventional rail. The Donghu test does not exist in isolation from that context. It exists as the research frontier of a nation that has already demonstrated, at massive scale, that it can build and operate high-speed transportation infrastructure. The question is no longer whether China can build fast trains. The question is how fast China can make them. And on the 17th of June, 2025, part of that answer became 650 kilometers per h-hour. Every second of that 7-second run mattered. Every millisecond of control loop response mattered. Every millimeter of positioning accuracy mattered. Every joule of energy stored in those Gauss-Inner banks before launch mattered. Every gram of the vehicle's carefully calculated mass mattered. Every coil in that 1,000-meter guideway, positioned to fractions of a millimeter tolerance. Every line of control software, every sensor in the measurement system, every component of the electromagnetic braking circuit, every single element of that system had to work simultaneously, perfectly, in 7 seconds. And they did. This is what human engineering looks like when it is working at its limits. Not the romance of it, the sweat of it, the years of calculation and recalculation, the prototypes that did not work, the test runs that were aborted, the software bugs found at 2 in the morning and fixed before the morning run, the coil that was replaced because its alignment was off by a fraction that no test equipment could even measure directly, but the control system's behavior suggested was wrong. The meeting rooms full of engineers arguing about deceleration profiles and braking force curves and energy recovery efficiency. The slow accumulation of knowledge, each run teaching the system something that the models had not predicted. Each lesson feeding forward into the next refinement. This is not a story about a moment of genius. This is a story about the patient, unglamorous, relentless accumulation of engineering competence applied to a problem that the rest of the world assumed could not be solved without 42 kilometers of track. And here is the truth that sits at the center of all of this. The truth that the 7 seconds and the 650 kilometers per HR and the 4-millimeter precision and the 220-meter stopping distance all point towards speed is not the goal. Control is the goal. Any system can go fast in one direction until it hits a wall. That is not engineering. Engineering is knowing exactly where the vehicle is at every moment. Engineering is being able to stop it, safely, predictably, within a calculated distance. Engineering is the ability to repeat the run, to do it again tomorrow, and the day after, and the day after that, with the same result. To learn from each run, to push the parameters slightly further, to build trust in the system not through a single dramatic demonstration, but through the patient accumulation of verified, reproducible performance. That is what the Donghu Laboratory achieved on the 17th of June, 2025. Not just 650 kilometers per h, our controlled, measured, precise, reproducible, 650 kilometers per h, with a positioning system accurate to 4 millimeters, with a braking system that stops the vehicle within 220 meters, on a 1,000-meter track that can be reset and run again. Japan spent 10 years at 603. China spent 1 kilometer getting past it. The next record will be 800 kilometers per h-hour when it comes. And it will come. It will be set on that same 1,000-meter track by a system that has been refined by every run since the 17th of June. Every data point collected, every control algorithm improved, every component stress tested and validated. The system learning, run by run, what it needs to be capable of in order to push the number higher. And somewhere beyond 800, the conversation shifts from kilometers per h-hour to what those kilometers per h-hour actually mean for human life. A Beijing to Shanghai journey that takes roughly 4 to 5 hours by today. Fastest high-speed trains, reduced to 90 minutes. A connection that currently requires a flight, including security boarding. The dead time of aviation, made faster by a ground vehicle. A world where the 500 to -1,000 kilometer journey, the range where flying is inefficient and driving is impossible, belongs to something that floats above a guideway on magnetic force, moves at the speed of a cruising aircraft, and stops so precisely that the error is measured in millimeters. That world does not exist yet. The Donghu test did not build it, but the Donghu test proved that the physics that would make it possible are real. That the engineering challenges that stand between a 1.1-ton test sled and a 50-car passenger train traveling at 600 kilometers per h-hour between cities, those challenges are finite. They are enormous, but they are finite. They are engineering problems, not physical impossibilities. The record stood for 10 years. Then it fell in 7 seconds. 7 seconds that represent not a shortcut, but the opposite. The concentrated product of years of rigorous, precise, exhausting engineering work done in a laboratory in Hubei Province by a team whose names most of the world does not know. Work done on a 1,000-meter track that fits inside the distance the Japanese record run covered in 10 seconds. This is what engineering is, not the announcement, not the headline, not the number on the screen when the measurement system confirms the peak velocity. Engineering is the 10,000 invisible decisions that made that number possible. The calibration, the iteration, the failure and the recovery and the next attempt. The 4-millimeter precision that nobody sees because all they see is the blur. Without the control system, there is no record. With it, with every sensor, every algorithm, every coil, every component of the measurement and positioning and braking infrastructure working exactly as designed. There is a vehicle floating above a guideway, accelerating beyond anything the world of rail transport had ever seen, and stopping safely within 220 meters. Without it, chaos at 180 meters per second. With it, a new page in history, written not with applause and crowds along a 42-kilometer track. Written quietly, in a laboratory. On a Tuesday in June, by a machine that most of the world had never heard of, on a track that most engineers said was too short to matter. 7 seconds. 650 kilometers per h are 4 millimeters of precision. 220 meters to stop. Those are the numbers. But the story is everything that had to be true. Everything that had to be built, calculated, tested, refined, and trusted for those numbers to be possible. If you enjoyed this video, please subscribe to the channel and leave a comment below. We want to know what you think. Will China have passengers traveling at this speed before Japan opens the Chuo Shinkansen? Is 800 kilometers per HR the next record? Or will someone skip straight to 1,000? The comment section is yours. Thank you for watching.